All right. Welcome back. Let's see. At the end of the last week, after the meeting with our client, we talked a little bit about testing, um, and there's several thoughts on testing. A lot of folks are moving towards that's the first thing that should ever be done. Just translate specifications into testing before writing any code. And then writing the code. The goal of your code is to pass those tests. Now there's different types of tests, and we just mentioned one of those types last week, black box testing, right? That we don't really care what's the implementation inside, what the code actually does inside, or how it accomplishes, how it's implemented. We only care on the behavior, looking at it from outside. Very much like if we step inside of any car, we assume that it has certain features, certain behaviors. As long as it has a standard interface, right? Just a wheel, some pedals, and a stick. Presumably, we can drive any car. We not really care, perhaps, so much at how it accomplishes this. So today we're going to look at another type of testing, structural testing, where here we do care about what's inside the box, how it does accomplish what it does. Since we'll see that no one strategy is enough, right? That they can all work together and complement each other. Trying again to see if whatever we're building is behaving as expected. In black box testing, we could throw at it lots and lots of data from outside and look at the behavior, and it looks fine, but never come to select a particular set of inputs that exercises the entire code base. Right, so the question might be, well, here we have some representative inputs and outputs that we're expecting, and somehow there's this part of the code that never gets executed, right? So it kind of begs the question: is why it's even there? Right? Is it even necessary? Was it a misunderstanding of the specification, or perhaps yes, that indeed has to be there, but for some reason we don't know enough about the problem to select representative inputs and outputs to exercise that piece of the code. So white box testing is tries to address this issue, right? Tries to look at the actual source code and try to look at it and say, okay, well, what are the various branches? What are the various if then else statements? What are the various while loops? What are the various conditions that would cause certain pieces of code to execute or not execute? Right, and if you have various Boolean expressions, what are the various possibilities, combinations of those predicates that would cause a particular branch to execute or not execute? Okay, so structural testing is looking at the source code, analyzing it, and see what are the conditions that would cover the entire source code and elicit some knowledge about whether the source code is correct or not. So it tries to cover the entire source code. There's several tools that allow you to keep track of how as you are executing your unit tests, how much of the total source code is being executed. Right, you need compilers that support this feature, right? That adds additional source code in the bytecode that we can use to generate reports like this, right? That count how many times a particular statement has been executed, and we would like to report on that to make sure that at least a statement has been executed at least once, right? That we have gone through a particular source branch at least once. Right? And most compilers today, most IDEs support this feature out of the box. So there's various aspects that can be measured. The simplest thing that we can measure is, are we hitting every single line in the source code? Right. That's the simplest way to have some measure that indeed we are stepping through each one of the pieces of statements. But that's usually not enough. It might be that the conditions by which we enter that piece of code might be in different conditions. So we also like to look at what are the various possibilities, or what are the various combinations of values that make us traverse a particular piece of software or a particular branch. So we want to look at statements. We want to look at the paths of execution. There might be loops that go through a piece of code several times, and you don't get a failure until you've executed many times a particular loop several times, or a particular path several times that would put the application in a particular state, right? That would cause a failure. So there are various criteria by which we can try and measure whether the source is good. Again, the simplest of which is statements. Checking to see if we are stepping through every single piece of statement. More commonly in industry, we try to look at branches. What are the various branches, if statements, loops, and the various conditions that cause navigation through those branches? That's the more common criteria. Have all the branches been exercised? So typically, it's not the place to start. Structural testing is not where we would start to see if the code is good. First, we would focus on creating good unit tests that try to partition the input data space to try to elicit, to go through the various use cases. Once we feel comfortable with our unit tests, we would then go on to try to see if run some static code analysis to see if we are indeed if our unit tests are indeed exercising every single statement, every single branch, every single condition. So it might be that even though we're happy with our unit tests, our structural tests might come back and say, well, you might be happy with your unit test, but you're only exercising 60 or 70% of your code base, right? What happens to the other 30 or 40% of your code base? Is it useless code, or is it code that should be there? And what is the health of that source code? Right? So first you would focus on unit tests, right? And then additionally you would run some static analysis or some structural test analysis. So for instance, here's an example that tries to solve the roots of a quadratic equation where it takes arguments a, b, and c and tries to figure out what are the various roots. Now, depending on how thorough you want to be on all the possibilities of combinations between a, b, and c, certainly it's an exponentially hard problem. Right? It's way too many possibilities of combinations of a, b, and c to try and find out where your particular function that finds the roots, where would it fail. Instead, it would be very helpful if you take a look at the implementation. Somebody wrote this, and we should if we look at the various conditions, if statements, while loops that are used to implement this function, it might elicit some ideas of what domain, what ranges of values would cause some problems. Right? So once we do have access to the implementation, we can start try to find out, what are the values of A, B, and C, right? That might be an issue, right? Looks like depending on the quotient, using the quadratic equation to find the roots x here. Depending on the quotient here, which is the square root, the square of b minus 4ac, right? Depending on the value of the quote of the square root, right? We might follow different branches, right? Depending on the combination of the square root and the value of a. And now we have some idea on are we exercising, are the values, all the combinations of a, b, and c, running us through all the various if statements, if-else statements in here, right? So let's consider just one of these. There's three different cases, right? For instance, depending on the combination of a, b, and c, it might be that the code takes us through one of the first if statement. With another combination, it might take us to the second one, and the third might take us to the default value. Now this is a trivial example, right? But if you could extrapolate, if you consider a very complex example, depending on your knowledge of the particular domain of the problem, selecting what values, input values, are relevant or not might be very challenging, right? Here, we know the quadratic equation is trivial. We can write it out in a single equation, right? And we can certainly start thinking about, what if the denominator is 0? What if the quotient, we try to do the square root of a negative number? So we certainly have some domain knowledge, right, on evaluating these types of equations. But certainly, if this were a fairly complex function, right, presumably computing something of a domain that we're not familiar with, right, choosing the input values that might test the various if statements, if-else statements, and might not be trivial. Okay, so it helps to go in the source code and look at all the predicates of all of these if statements, right, and the while loops and whatnot, and what causes what conditions cause it to navigate your code to execute either one or another branch. Here we can certainly choose a couple of simple examples that might cause various branches to execute. But let's consider just one of these cases when the square root is 0 above, right? When q is equal to 0, and once we have that, there is an if statement that deals with that particular case. If it's 0, then the result is simple enough. So it's just minus b over 2a. That's the final result. And in that particular case, right, we would like to make sure that when we are dividing, that the a is not 0, right? So certainly that's one case that we might consider, right? So looking at the source code certainly can inform us, right? What are the various edge cases? What are the various boundary cases, special cases that allow us to partition and select the input values, right? As opposed to just considering all so many various billions of various combinations. Looking at the source code certainly can educate us on what to choose as input. Okay. So certainly looking at the source code here, we realize that indeed we need to handle 0 is certainly a equals 0 is certainly an important value to consider, and we can only know that from looking at the source code. So the program structure can inform us, right? So black box, for some reason we might not be choosing a equals 0 as an input. Again, maybe because of the lack of knowledge of the particular domain, right? Here certainly is trivial enough to understand that a equals 0 is an important edge case. Oftentimes it's hard to capture these edge cases, these special values by looking at source code. Oftentimes it's easier to reinterpret or represented in an image like a graph or like a control flow graph that might make it a little bit easy to understand what's going on here, right? Understand what are the various transitions, what are the various operations and Boolean expressions that and comparisons that cause the application to branch off into various execution paths, right? So control flow graphs allow us to more easily identify these cases. So by representing predicates with their own symbol, representing statements with their own square symbols, and now it makes it a little more easier, right, to say, okay, well, that condition of q equals 0 or q greater than 0, a different than 0, certainly those are of interest to us, okay? And we'd like to be able to make sure that we are indeed going through all the paths, right, and visiting all the various nodes. Now these nodes here, there's a one-to-one mapping, right? Here's an easy one-to-one mapping between these nodes and the actual source code. Since the source code is so trivial, there's almost a one-to-one mapping. More commonly, the operations here in the double where we're computing q, or where we're computing the two roots and whatnot. Oftentimes, those nodes are collections of various statements, right? Right now, over here, we're representing one node represents one statement, right? But more commonly, when we talk about a control flow graph, we usually group various statements in one single node, with the idea that if you have coverage on your graph, typically you have the same coverage on the statements, right? That this is an abstraction, right? This is an abstraction of the more low-level implementation. Although at some point also this was an abstraction, right? Functions and classes and inheritance and public and private methods, right? All that is an abstraction, right? Object-oriented technology in per se is an abstraction layer. Certainly was so when it was invented. And here's just another level of abstraction that allows us to think about the problem just at a little higher level. So control graphs allows us to consider first the individual nodes and also the various paths and edges that transition between the various nodes. Right. So there are various parts that we can consider individually. Right. We can consider the nodes themselves. Do we want to make sure that we visit every single node? Do we want to make sure that we visit every single edge? If this had a loop and going back up, do we want to also consider various paths, right? That we loop up again, and then we follow a completely different path, right? Might different paths put the program in a particular state that wouldn't otherwise do if it wouldn't loop various times. Oftentimes, unit tests are not as thorough as that, right? They treat the application as a function, right? You put in values x, y, z, and you expect the same result for the same input. Okay, so they're typically stateless tests. Right? Unit tests are typically stateless tests, whereas structural tests and integration tests might go a little further and look at the behavior of an application over time, right? As the application changes from one state to the next, right? So that as you traverse various paths, right, you consider the application at various states. Now different. If you consider just the nodes, or if you consider only the edges, or if you consider the various paths, right, you have different criteria by which you consider your test a good enough test, right? That you have done a thorough testing effort, right? And each one, each criteria has different aspects that it is concerned about. Control flow graphs certainly implement everything you might expect from a high-level programming language, procedural language. We have certainly all the major programming structures are there: the while loops, the do whiles, fors, the conditionals, and whatnot. And they presumably they map a one-to-one to some low-level language implementation. So here's a running example that we're going to visit throughout the lecture. It's a very simple program that decodes the URLs that are passed in through a server, right? It's a very common algorithm, right? When you pass when you type in a URL, it is encoded in such a way that it can be transmitted as just plain old text over a network, right? Over to a server, and the server needs to decode that URL back into plain old text, right? So the URL usually encodes certain special characters as using some meta characters. For instance, all pluses are converted into plus signs. Any special characters are converted into percent, and then their hexadecimal equivalent, right? And so you can pass through any data in the URL, but it is encoded so that we don't have we can serialize it over HTTP. On the other end, when the server gets a hold of this URL, it needs to be able to reconvert that encoded string to plain text, so it can parse out the query parameters, any session information, and so that it converts it back into just plain old ASCII. So here's a very common implementation of this decoding. It's called the CGI decode, and it takes as arguments the original string, and it returns a decoded string. And here we've just pointed out a couple of branches, a couple of conditionals, and we've pointed out several of the if statements and the else, and the various operations. Some of them are loops that iterate over the pointer of the input. And they build an output string, okay? And depending whether it finds a percent or it finds a plus sign, it converts it into either a space, or it converts it into its ASCII representation from hexadecimal. So we've labeled the various parts of the source code so that we can then refer to its equivalence graph, control flow graph. Right. So these are the main source points that we were looking earlier. Again, several statements have been collapsed into a single node, right? Like the 3 lines of code in node A, and the 3 or 4 lines of code in node G. And the various branching that occurs from different nodes are being represented here on true-false navigation between the various branches, right? The various nodes. Okay, so this is a little bit easier to visualize, and then take a look at some combinations of input and see how the paths, right, the various nodes are visited as the input strings are being interpreted, right, as they are being converted from their encoded to their decoded representation. So if you consider a couple of input strings, such as test, you follow along as each character is being parsed. We see that it follows the left-hand side all the way down to OK. And iterating, right? Every time it moves over to the next character, it doesn't find any special characters such as percent. It doesn't find plus. It doesn't find any of those special characters. So there's no need to convert these special characters to plus or ASCII or whatnot, right? So it looks like we never look at the branches in nodes E, G, H, and I are never visited, right? Because we don't have the percent or plus on any of those meta characters. Okay, so someone who might not understand or know enough about the domain, right, of URL encoding might, provide a plethora of inputs of various words and paragraphs and tons of lorem ipsum and lots of data that, as far as they're concerned, is a wide representation of text, right, that would test this. But be completely unaware that the entire purpose of this would be to convert pluses and hexadecimal code into their ASCII equivalents, right? Not knowing this, they might not they might not actually provide useful test cases that would exercise the other nodes, G, H, I, and E. And this is a very, very common problem in industry. All right, this is a very trivial example, but it's a very, very common problem in software development teams. Right? So it's becoming more and more important for teams to run their static code analyzers that let them know, hey, there's 20% of your code that you've never even tested. Right? It's there sitting there, and none of your representative data, as far as you think it's representative, is not actually exercising a huge chunk of your source base. Right? So if we consider another example where we do have one of the meta characters, the plus sign, we see now that we are now exercising an additional branch here, that we are converting the plus to its equivalent space, right? So we have a little better coverage, right? We look like we are going through some more pieces of the source code than we were earlier, since again we might have knowledge that plus has a special meaning here. If we add the percentage, the percent, and use some hexadecimal value there, we see that we have an even greater coverage of our source code. We go through the branch that parses the percent and then looks to convert 3 and D into its ASCII equivalent, right? Multiplies 3 by 16, and then the value of D, its value. So 16 plus 3 times 16. That would give you the ASCII value, and it gets converted into we grab the character and into its solution decoded value. We still have another node that we haven't covered, and those are all the negative cases, right? When we give it bad data, when we give it some bad data that would cause the program to fail, right, or to come back with something bad, something that is not convertible, like for instance percent and G, right, a non-hexadecimal value, a non-hexadecimal character, and this would be encountered and interpreted as an error. It's a string that cannot be converted since G is not a hexadecimal value. And finally, we see that indeed we were able to identify that and return a 1 for failure. OK is the sentinel that we use to keep track on. I think we said it somewhere here. Yeah, so the value 1 returns, it's a bad hexadecimal digit, is the value that is returned by the decoder. So there we go. We have 4 representative input strings, right, that presumably is able to exercise our entire code base, right? It goes through all the different branches, but even then, it's not as thorough as we might want to consider this, right? Even though we can feel confident that we have exercised all the various statements in our source code. We might have 100% coverage statement-wise, right? But not necessarily still feel confident that that all bugs might have been averted, right? So depending on your criteria, you might feel that this is good enough, right? It's adequate. But there are various criteria that we want to consider. The simplest of which is, have we gone through all the statements? Right? Is that your criteria? If your criteria says I have input that fully exercises every single statement in my code. Okay? If that's your criteria, then 100% coverage of your statement then might be good enough, right? And then you're all set. But that is not the only criteria. There might be several other criteria that become more and more sophisticated, more and more involved in your knowledge of that particular domain. So typically the criteria might be as a statement, all statements must be covered. Right? Perhaps that is your criteria of success, right? That is the simplest criteria. And in our case, those 4 input statements, input strings, were successful, or was successfully going through exercising the entire code. If that's your criteria, then your measure of success is comparing what the ratio is of what are the total number of statements that you're exercising, right? That your unit tests are exercising over all the total number of statements, right? If it tells you that you're only exercising 80%, that means that you have an 80% success rate, right? That you're only hitting 80% of the code. So if you have 1,000 lines of code and you're only hitting 800 lines of code, then your success rate is 80%, and that is the level of criteria. That's how good it measures your particular criteria. But that's not the only criteria, right? Let's first look at using this input. Let's go back to the same 4 inputs that we were looking earlier and measure based on our success criteria how we're doing. With tests, we see that we hit 63% of all statements, right? That we've hit at least once, right? It might be that we hit the same node several times, right? So here the success criteria is that at least once we've exercised a particular statement. If we now consider the meta character plus, we see that we're adding just a little more in the statements that we're going through. So our criteria goes a little bit higher to 72. If we use the meta character percent and some hexadecimal value, we see that our criteria measurement of success goes a little further since we've exercised 2 or 3 more of the nodes. And finally, when we consider the negative case, where we provide a bad case, right, that percent and then a non-hexadecimal, we'll see that we've exercised all the statements, right? So as far as we're concerned, right, we have successfully tested our code, right? That we have considered all the statements, and we can identify errors in our source code because we've gone through all the statements. Most IDEs, most compilers support these features. In Eclipse, is as easy as one menu selector. You can say, just give me the code coverage, and it'll run your unit tests, right, and tell you, how many statements have been exercised, right? In GCC, in C++ compilers, there's several flags that you can add to it, and the compiler will add additional bytecode into your source code so that it can count, right? It can keep track of how many times has a particular line of code been exercised, right? Just like when you debug, right? You use a particular flag that allows you to add additional bytecode that allows you to step through the code, right? Put breakpoints and whatnot. Well, there's other flags like ftest coverage and profilers, right? That add additional code in the compile code that can generate a file, right? That gives you the coverage, right? .gcov file. When you open up the file, in there you can see that it'll give you counts on how many times has it gone through each line of code. So the while loop has taken 38 times, the if statement 30 times, the else if 29 times, the pointer when you're done when there's no conversion, it has done it 26 times. For various tests, unit tests that has gone through, right? There's some notice that it has dashes in there. Those are executable code that cannot be executed, right? Such as else statements or else if, right? Else's cannot be executed, so it does not there's nothing to do there, right? It's just or just curly brackets, things like that. If it finds any code that has not been exercised, right, that it has not traversed through that particular branch or has executed a particular set of lines of code, it'll highlight it, with big hash signs, right, saying, hey, these lines of code have not been executed. Be careful. Go back and perhaps tweak your unit tests so that it does not it makes sure that it goes through that piece of code. Okay. Now, yeah. So depending on the criteria that you choose, there are different things that you need to consider. The one we've been looking at is the one down here, the statement testing, right? That's way down there, and this is only one of a family of criteria that can get more and more sophisticated as you introduce other things to consider. Right now, we're only considering that I would just want to make sure that I'm stepping through every single line of code, right? And that my unit tests exercise all the various statements in my code. But certainly, if you make your criteria a little more sophisticated, there's a plethora of families of various criteria that are available. That we're going to consider just a few of these, right? First, now the hierarchy is organized in such a way that criteria at a higher level, right, assumes or is implicit that criteria at a lower level are also being tested, right? That if you test, for instance, for branch testing, that already includes the fact that you'll be testing for statement testing, right? You don't have to do both by testing branch testing. You're already doing statement testing. Right? If you as we'll see in a minute, branch testing considers all the various branches that you can branch off in your if statements, in your while loops, in your gotos, and if you're testing all your branches, it is implied, right, that you're going to step through all the statements. Right, so it's not an and, right, but it's an or, right. So the branch testing, we say that it subsumes or it's implicit, implies statement testing, right. So yeah, so the one we were just looking at it, we just looked at is referred to as statement testing, and it's certainly the simplest one to implement. Now a more thorough testing is to consider a different criteria, right? And it's named as the branch testing, right? It's a completely different criterion that where we want to make sure that we go through every single branch, right? Wherever you have a condition, wherever you have a decision point, right? Whether something is true or false, we want to make sure that we've gone through each one of the branches, right? It's a little higher level than statement testing, but if you do branch testing, you are also implicitly also doing statement testing, right? So we say it subsumes or it's implied that you're doing also statement testing. So just to illustrate the difference between the two, and where one would add additional information where the other one does not. Let's consider let's consider the same example we looked at earlier. Say we wrote the code and we have all these if statements and while loops and conditionals that evaluate to true, false, and whatnot, right? And you have all these branches and branching out to various nodes depending on the values of the condition. Say we didn't write statement F, whereas the default case, right? The default case would be that we don't need to convert anything, right? It's not a plus sign. It's not it's not a percent sign. It's just a character, a normal character converted to a normal character, Right? Say we forgot about that and we don't have that default case, right? That else statement. So we didn't have, for instance, we didn't have a node F, right? We forgot to do it. So if we take the string, the test string shown there at the top right, we would notice that according to statement criteria, that particular string would exercise our entire code, right? Because notice that we have plus signs and ampersands, and we have lots of different, looks like random characters, but actually has some meaning, right? It has a lot of meta characters like plus and ampersand, and we have lots of good and bad hexadecimal values, right? We have a 0 and a D, which is a good hexadecimal value. Then we have a 4 and a J, right, which is a bad hexadecimal value. So it looks like we're exercising our entire code as far as the statement criteria is concerned. We have covered our entire code, right? But if we instead use the criteria of branching, right, we would notice that, hey, wait a minute, all Boolean expressions have a true and a false, right? And it looks like for all of them, you are considering the true and false results of all these predicates, but except for this else if. What happened to the handling when that is false, right? If we use the broader branch criteria, we analyze it again, and we analyze it and we run an analyzer that instead of using statement criteria, it uses branch criteria. It would tell us that you only really have 87% of the code is covered, right? Not yes, definitely you're stepping through all the source code, but you are not considering some of the branching possibilities, right? All of them have you're treating both cases of true and false for the while loop. You're treating true and false cases for the if C is a plus sign. You're considering the true and false if the digits are not negative. So you're doing all that except for the else if, right? Of when the C is a percent, right? You're not considering when it's not a percent, right? When it's not a percent, you're not treating it. So a code analyzer would come back and give us a B plus as opposed to an A if you are considering the statement, right? So again, code analyzers allow you to elicit some of this information, right? It might be that the specifications were wrong, right? That nobody ever told you how to handle certain edge cases, right? That it's a edge case that the business analyst or even the business owner wasn't even considering, right? Perhaps it's something that never happens, okay? Nevertheless, it should be explicitly considered, right, as perhaps a don't care, right, or this never occurs. So if it does occur, something is wrong. This allows you to identify maybe flaws in the original specification from where this code was originally derived from, right? Right. So yeah. So it's very, very useful to feed both the specification feeding the unit tests, but the unit tests and various tests also feeds back into whether the specification is correct, right? It's very common that the specifications, when they come to us from our clients, they only consider the happy path, right? The steady state behavior of a system, and do not consider many of the edge cases, and they're only discovered when we start creating some of these test cases. So here, again, if we provide A, B, and C, we would and we put it back. We put back F. A, B, and C would execute and make sure that we're taking into account when it's not a percent, when it's not a plus sign, when it's just a regular character, and we're just copying it over to the decoded result string. Okay. Right. So branch testing, the criteria in branch testing is not the statement. We're not so interested about the statements. We're interested more on, has each branch gone through at least once? Have we gone through each branch at least once, right? Considering the various possibilities, at least true and false, and the coverage, our measure of success is, well, look at all the branches, right? All the if statements, all the while loops, all the for loops, and all the conditionals, right? Where you're comparing something, whether it's equal, greater than, less than, or whatever. Look at all the predicates, and for each one, you have a true, false. Have you executed all the possible branching mechanisms? Are you going through each one of them? And if you consider branch testing, then by default you're also doing statements, right? You are going through each statement in your original source code. So this is the most widely used criteria in industry, although there are even more sophisticated criteria, which we'll see in a minute. But why this is the most widely used one out there. Right, so we look at these two, right? Branch testing and statement testing. These two over here, statement and branch. We can also take a look at the actual predicates, right? If we look at the predicates, it might be that that depending on how many variables you have on a predicate, certain values for the variables in the predicate might be causing branches to go true, false, meaning you are successfully navigating all the various branches, all the possible branches, but it might be that because of the Boolean expression of how they behave, that you might be short-circuiting some values, might be short-circuiting all the various possibilities of some other variables, right? And maybe some of them are always true, and if it's an or statement, it doesn't really matter where all the other ones are, right? So even though some of the other values of the other variables might cause a failure in your source code, it might be that you're never successfully testing it because the values that you're choosing make the other predicates always true, and they short circuit the entire rest of the predicate. So basic conditional testing considers each predicate all by itself. Excuse me. And it takes a look at all the variables that cause the predicates to go true or false. Considering all the various possibilities in the truth table, and sees how does it cause the application to navigate. So this is a much more thorough testing case because it considers all the various possibilities of the input. So for instance, here in the example, in this example of the in the decoder, right? We have a Boolean expression where we have an or, right? We have a digit high and digit low. These are the two characters that are meant to be representing some hexadecimal value that need to be converted into an ASCII representation. And it could be that just one of them, right, digit low or digit high, either one of them might be causing this to always be true, right, or always being false, regardless of what the other one might be doing, right? It might be short-circuiting the entire Boolean expression. This one is a little bit too trivial, but it might be that the whole behavior might be based only on a subset of the variables, right? And many other variables, part of the same Boolean expression, are not even being exercised, right? We're not even considering them. And as far as branch criteria is concerned, you are going true and false, and you are considering all the various possibilities of navigating through all your branches, but the true and false navigation is only being dominated by a subset, right? A subset of the variables that are being considered here. Okay, what conditional testing tries to do is, hey, what about, let's look at all the possibilities of combinations between all the various variables that could cause problems. We're looking to see for every Boolean expression, right? What are the truths, right? What are the various possibilities of true and false, and just list all the possibilities, and perhaps in a truth table, right? And although it might be impractical if you have way too many variables, it could be exponentially hard to consider all the possibilities of your input. Nevertheless, it would educate, right? It would educate what cases you should consider. Now, these two are completely unrelated to one another. Just because you're successfully have a good branch testing, that doesn't necessarily say that you have also basic conditional testing, or vice versa. So what we typically like to see is how those Boolean expressions, all those various combinations, how do they affect the branching? That's why we can combine the two, right, into a higher criteria called the branch and condition testing, right? How can we combine the two, the branching and the condition, to see what the various predicates, how they control the flow of the application, right? Now it might be that you want to be as thorough as possible, and you write out all the various variables and you consider all the various possible edge cases. Typically, that's very impractical. It could be that you have millions of combinations of your variables. And it would be very impractical to try out. So, for instance, only considering these very simple Boolean expressions where you have A or B and C, or D and then ANDed with E, just looking at this, comes out to be 13 possibilities. Some of them, the values have dashes because excuse me, the other variable, like A, is short-circuiting the value of B, right? So it doesn't really matter what value of B is in test case 1. That whole subset is true when A is true, or the same thing with C. When C is true, it doesn't really matter what value of D is, right? And those short circuits are the ones that we're concerned about, right? By having a true there, it short circuits the entire rest of the Boolean expression, and its effect of the other variables is not being considered in the flow of the application. So this might be somewhat impractical to consider every single possibility of the variables. So what we want to be able to do is identify a subset, right? A subset of these very, very large number of possibilities, and identify which ones are really representative here, right? Which are the edge cases that are more representative of real case scenarios, and we might identify perhaps that only half of them might make sense, right? That the other ones just never happen, right? It might be interpreting some use cases that are not really existence in the real world. So yes, we like to be able to identify only those important combinations. So we call this the MCDC testing. That it's a subset of the compound conditionals, that where we only identify a subset of the conditions that are important to us, right? We consider the compound and the boundary, interior testing, and all those above the dotted line. We refer to them as theoretical, right? As in yes, it'd be great if we could if we have all the time in the world to be able to test all the possibilities, but we don't, right? So in practical terms, together meeting with the business analyst and meeting with the business owner, we identify which of those millions of possibilities are actually practical, which one are actually representative in real life. So it might be that we only have a small subset of the various test cases for a particular condition. And we want to see how that particular various tests cause the condition to be false or cause the condition to be true, right? To make sure that we have branching, that it's going to branch one way or it's going to branch another way, right? We identify some subsets that cause it to be true, cause it to be false, and they are representative of real life. So it might be that we identify that given this particular Boolean expression, that only these 6 are representative in real life, in real use cases. Okay. Path testing is another theoretical testing criteria where you want to consider all possible paths, right? Especially if your application has loops where you are iterating over several, a collection of data, and every time you iterate, right, there's various if statements and nested conditionals inside of that while loop that might take you different paths, right? So if you're looking at a particular instance of an object, depending on the values of the state of that object, might cause the path to go one way. In the next object, in the next iteration, it might cause it to go in a different way. Yes, right. So what path testing? The idea here, the criteria is that have you tested all the possible paths? Right. You're iterating and you're going through one path, and as you come up, right, and then you come down in the next path, are you going a completely different path? Right. Have you considered all the possible paths? Now, excuse me. Like compound conditional testing, this is also unrealistic, right? To implement this kind of testing in practice, right? It's just, again, you have an exponential explosion of possible paths that you can take in your code. It's just not practical to implement. Right. So you might have lots and lots of different nodes, and as you're iterating, right, you might want to consider one path and then maybe another path, and soon enough, right, you have just a way too many possibilities of iterating over this in a loop. So instead, we look for something a little bit smaller, right, where we try to identify what are the boundaries of the loops, right? What are the causes that make us go into a particular loop and allow it to stop, right? And we might consider where the changes in the state of an object, if they have lingering effects on the on later iterations of the same code. If they don't, then there's no real need for looping more than what you need to be able to consider a particular path. So typically you try to identify and unwind the loop, right? So that instead of looping, right, and going back up to and iterating through a different path, is you identify that path and you unwind it, right? You write it out as if it were a single path, right? And just go through that path once as opposed to looping through multiple times. Where for instance, again, going back to our original CGI decode example, we do have a loop as it's iterating over the input string, right? Where we have the while loop in node B, and it's still looking at the pointers of each character. And as it's walking through the characters, we do have several paths, right? It could be that we have a character that cannot be converted into ASCII. It could be that it's empty. It could be that it's a plus. It could be that, so depending, as we iterate over the various possibilities, we might be taking several paths, right, as we're looping. So what boundary interior adequacy does is that it tries to unwind all these possibilities, right? So as you go back up from the L, going back up to B, instead of considering the path again, you just copy the same nodes and you're copying down to see what all the various executions, and then you consider as if it were a single path, as opposed to a loop that might be harder to test, right? So this is a subset of the more generic path testing, right? It's something that's a little more easier to actually implement. Again, what you want to avoid is all the just exponential explosion of combinations that this testing introduces. Right? All of these try to deal with this exponential complexity. All right.